Hey guys, in this video I'm trying to give you a little bit more intuition or maybe understanding of what a channel response means. So here I have my input signal, which is blue, and it's going through a channel, and my yellow is the output signal I'm receiving at the end. Now here it seems like the magnitude of my channel response, or h of omega, is 1, and the angle or the phase lag of my h of omega is 0. This is because the amplitude of my yellow and blue waves are identical, and the phase of my yellow and blue waves also look identical. They seem like exactly the same wave. So in this channel, the channel responds very well, essentially, to the frequency this blue wave is at, which is currently about 10 hertz. At 10 hertz, h of omega, where omega corresponds to the 10 hertz in radians, is of magnitude 1 and phase 0. Now let's see what happens when I try some other frequencies or some other omegas. Let's see what happens to my channel response. So now I've just bumped the frequency of my input signal to 100 hertz. I'm going to zoom in a little bit, and here you can see that my blue wave, or my input signal, is still essentially in phase with my yellow signal, but the magnitudes are different. My yellow signal, which is my output, or y of omega, is smaller in amplitude than my blue signal, which is my x of omega. That means that h of omega at 1 kilohertz is less than 1. My amplitude is smaller. Let's see what happens when I increase the frequency again. And I'll zoom in so you can see what's going on. Now my blue signal is at 10 kilohertz. And my yellow signal, which is my output, is so small. It's like, you can still see that it's kind of waving, but the amplitude is tiny. This means that the magnitude of my h of omega at omega equals 10 kilohertz must be really, really tiny. So I can go to another, zoom out a little bit. You can see I've moved back to 1 kilohertz, and the amplitude change isn't too bad, and I've moved back to 100 hertz, and now it's essentially the same magnitude. This is just showing you that for a channel, it can react differently to inputs of different frequencies. At some frequencies, it can amplify your input signal, make the magnitude larger. At some frequencies, it can keep it the same as you're seeing here. And at some frequencies, the magnitude of h of omega might actually be less than 1, and you're attenuating your signal. You're making it smaller. This is why we want to know the frequency response of our channel. This is why we want to find h of omega, because we want to know what will happen to an input signal as it goes through this channel. If you actually want to know what's going on in this channel or what this channel is, I have my input sine wave coming in with this red wire, goes across a resistor and a capacitor in series, and then to ground. For my input signal, I'm just measuring the input against ground, and then for my output, I'm measuring the voltage across my capacitor. This is an RC circuit, and it's actually an example of a low-pass filter. which is why when I cranked up my input sinusoid to really high frequencies, we saw that the amplitude was really attenuated in my output signal. This kind of filter, the capacitor, allows lower frequencies to pass over it with a pretty intact magnitude and drives the amplitude of higher frequencies down. And that is a rough implementation of a low-pass filter, actually, and was demonstrated earlier in this video.